everyone, it's Judy Warner. Welcome back to this week's Ecosystem Podcast. Today, I'm joined by Murthy Upmaka of Keysight. We're going to talk about all things wireless technology. He is going to talk about both the promises and the pitfalls of 5G and what's on the horizon for 6G. He also talks about why it's so important for engineers like you to lean into the new era of digital twins and shift left mentality. Now let's jump into our conversation with Murthy Upmaka. Hi, Murthy. Thanks so much for joining us today. I'm really looking forward to learning from you today and sharing all your knowledge and insights on wireless technology. Before we get started, can you please introduce yourself, give us a little bit of insight on your background, and then what your role is at Keysight Technologies?
Well, let's start from today and then go back. Today, I am a solutions engineer, and we have in our Keysight, we do a lot of measurements as well as we do software that helps the people to design electronic systems. And I'm more focused on system level simulation and modeling. We do have portfolio of our products that help design circuits, model the devices, and then even we are expanding into quantum and then all those uh, frontiers that are coming up. But mostly my focus is some system level, high system level. I did work on circuits in the past. That's where I started, but I moved into the systems in the past 10 years, 10 15 years, more focused on this, and that's where I am. So before that, my education, I by education, I have a PhD in physics, and then I had the opportunity to take a little bit sabbatical from my first job to go to and then go and then do postdoctoral research. Um, it's interesting. I did my postdoctoral in terahertz. That is going to be 6G in
That's
now.
crazy.
So it's a little bit linkage with what I did.
What are some of the um, great and cool applications you're seeing? What are the challenges in our way? And just where are we with 5G and then looking ahead to 6G?
Yeah, the 5G in general, the communication is something that we cannot just fathom what it was like 30 years ago versus what we have today. Um, I mean, it's unimaginable. I can lift my phone and then talk to anybody on the other side of the globe, right, or anywhere on the globe, as long as they have the connectivity. And then I can transmit videos. I can communicate to them. I can share files, and then if I can sit at my home and then do my job, that's what I've been doing for the past 25 years. And then most of the times I can move out of my office and then still be conducting the job because of the wireless technologies. It's very cool. And then even for executives, the cool thing is they can approve on their phone the the purchase order or anything. It's a legal document, but we can do it on wireless because of the security it provides. So there are a lot of cool things that are happening for the business side, but for the people that have never experienced, they don't have to know anything about the wireless, but they can still post their videos on the WhatsApp and then TikTok and then Instagram. It's unbelievable how much the technology has come in. um, uh, the tech, what is amazing to me is not the coolness of this, but what is the reach it really reached the common people in the world.
Right.
um, Yeah, I come from India, by the way. Basically, from I was born in India, but I've been U.S. citizen for a long time. When I go there, I see people, common, very ordinary people that probably can't even, they I can't think that they can afford a phone, but they do have a small handset in their hands, and then they're able to communicate. And then the amount of services that it has enabled them, the economies can change because of the wireless technology. That's
You
the
bet.
coolness I see, the reach to the common people, and then changing the lives of the people. That's the coolness. Of course, on the higher end side, it's so cool that um, with this technology, what we can do, the to begin with, of course, we are still to work on that. That's why we'll talk about a little bit about the 6G promises. The 5G promised, oh yeah, you can download in 10 seconds the movie, entire movie, and then you
Right.
can watch, or you can play games. They, of course, that is happening. And then the other promises it made were like doctors can do remote surgeries, and then the cars can do autonomous driving because of the 5G technology. There were so many very cool promises were made, and then in fact it's going to be possible. Of course, any technology has its hiccups. Of course, 5G has hiccups even after 10 years. So that's a different story. But a lot of promises are fulfilled nowadays. Compared to what I could do 5 6 years ago. Now my download speeds on my phone are certainly much more. I can press a button. I can see certainly open up a 10 megabyte PDF on my phone. I can read it, or I can watch a video. The experience is better, much better. But has it been fulfilling all the promises it made? Looks like no. The It's like you set an expectation, but you're
Right.
not meeting it, right? Then the other people, like the user experience here is the biggest thing, user and industry, both. So the
Right.
user experience is what the 5G promised me, that I can just push a button and then I can just get this instantaneously on my phone. It is not happening. It is not happening. We'll dwell into that as well in our discussion today. But there are a lot of things were fulfilled in 5G, but there are many things that have not been fulfilled. So it's a mixed bag of promises and fulfilled promises and not fulfilled promises in 5G world.
Well, and of course, there's the military, there's radar, there's satellites in space. I mean, it's such a far reaching thing, but we don't always, as consumers, we don't always stop and think about what it takes to deploy these technologies. And of course, our audience are engineers who both use this technology and they're being tasked with deploying it, which is a whole different perspective and why I wanted to talk to you about these today. So the length of development in your mind, let's talk about the trends in development and maybe what some of the obstacles are and the opportunities. And I always like giving our audience, which you've started out beautifully, which is sort of giving us a state of 5G, right? And then peek over the hill a bit and see where 6G is going. So let's talk about that first. Like what are the shifts in the trends and developments of this technology? And let's also talk about ways that Keysight and almost every other company I talk to on this podcast and beyond is talking about shift left or the digital twin.
Yeah,
So,
yeah.
all right, let's talk about that. That's a
That's a
handful
big
I just
trend.
gave
Thank you
you.
for bringing that term. Shift left. What do you mean by shift left, right? Um, so there is, fortunately, there is a research paper from Air Force Research Labs some time ago, and they said that imagine there is a x-axis where as you progress on the x-axis, the cost of corrections in your system keep increasing. On the y-axis, it is the how much you know about your system, your confidence in your system as you're developing. So there are stages along the x-axis. We call them concept. You start with a concept in your mind, and then you start somehow calculations. We call them modeling and simulation, but
Mhm.
still people use Excel spreadsheets for. That's why I can I can even call calculation. And then the third stage is you put the things into a prototype, and next thing is to do a limited production and then final production, then deploy it into the field. So these are all the stages that we are any product, any system product has to go through. And what they found is your confidence in the system, in the legacy way of doing things, your confidence will exponentially increase, very steeply increase once you get into the prototype. And then you actually build, you go to the lab, you test it, your confidence suddenly is steeply increasing. And then it will go even further as you start into the manufacturing and your confidence of being able to produce at the required perimeter of the cost, and then deploying it. So what we have seen in the past is your confidence is not so much in the beginning, not at the concept level. Maybe concept is you don't expect too much confidence, but at the simulation and modeling or your calculations are not very accurate because you're taking shortcuts. You're making too many approximations. You're putting your things into your spreadsheet and then, okay, let Excel spreadsheet calculate for it. But these are complex systems. We need to be able to do more detailed analysis before. And the previous analysis, the legacy way of doing things, let us say we found a problem at the end of the prototyping. We went to the lab, we tested, and then our confidence is high. Because of that, we found the problems in the system. Oh, yeah, it is not going to work, right? That's very usual. And the only way you can correct is go all the way back and then do the spin. This is called in the world of electronics called spinning. You come back, do
Right.
another iteration, and
Yeah.
the
You spin another
correction.
board and you spin another board. And
Yeah,
during that time, you're throwing out boards, chips that can't be recovered.
yeah,
And um, without modeling and simulation, where you've correlated the math and you're trying to get your simulation and the physical product,
right.
it's like playing whack-a-mole, which is why we have to go into 3 or 4 spins, right?
Yeah, yeah.
Because, and I always like my friend Eric Bogatin always says, "Hope cannot be part of the design workflow."
Right, right.
So, I think you're making this case, you're starting
Yes.
to make this case anyway,
Absolutely.
so
Absolutely. You're right. So, what does it mean by shifting left? What are we shifting? We are shifting that steep confidence increase to the left. It happens much later in the legacy way of designing systems. So, by moving it to the left, you are moving that all that into the simulation calculation time, what we call. And so if you can model accurately, if you can simulate accurately, you know about your system already without even committing a penny on buying any hardware, right? So if you know that, then even if you have to take some correction, I mean, of course, simulating in the computer doesn't come free, right? It has some costs associated, but not as much as to the later stages. So you can correct it quickly, easily, and then your confidence level is so high that you go and then do the prototype and then finally and then so this is the trend that is happening, right? So everybody wants to shift left, calculate more. The phrase we all know: measure twice and cut once, right? If you keep
yeah,
cutting, you need to bring a new
right,
one to keep cutting. Don't cut
right.
it, just measure, keep measuring, keep simulating, understand your system very well before you can indulge in committing and then go to the lab. It is going and testing in the lab is not going to be eliminated. So the thinking for the engineer so far, anyway, I have to go and then test. Why do I need to simulate? Let me go and then do the testing and correcting. That is a hidden. There is something that is hidden that we are not realizing. Probably, hopefully, the industry is realizing slowly that there are hidden costs. There is a hidden inefficiency the way that things are done. So there, everybody is trying to increase the efficiency of the developing the systems. Shift left is a big concept going there. On top of it, when you shift left, the byproduct is you have a model, you have a system that you are building in the computer. That is what we call digital twin.
Mhm.
So why So what people are doing even there, some companies, some people, some groups are building good models in the computer, but once they go into the lab, they forget about this. Just leave it out and then proceed with testing and manufacturing and then operations, everything. No, don't stop there. You have a beautiful model. We can call it as a digital twin. Now use the digital twin to improve it through the stages of prototyping, through the stages of manufacturing, through the stages of deploying. Even after you deploy, there is a lot of learning. So please bring that back into your digital twin. Make it such a wonderful, accurate model. It behaves almost like the system that's out there. I want to share, the digital twin, the best digital twin, the most expensive, I can tell you, was developed by Northrop Grumman for the James Webb Telescope, right? When
Oh,
they
I
launched,
bet.
yeah, they launched 3 years ago. It was project overruns, and then it took 10 years more or even more. But once they launched, it was such a beautiful thing. They predicted everything, how it should go. And then, so at one, this was on a beautiful January, Christmas time, right? They launched 2 or 3 years ago, I believe. And once the satellite goes, once the rocket goes, and then it start dipping. I thought, why the heck it is dipping? They said that is by plan. By dipping there, they are going to save the fuel on the satellite, which is very valuable. So look at this. They modeled and then it just imitated what they did. So when they did it dipped, they were happy that it's not falling. It is actually by design. It went down and then it saved a ton of fuel. So now we have this wonderful James Webb Telescope in the space, and then we are seeing a lot of things that it's improving our understanding of physics, etc. Anyway, that's a different story. I don't want
Well,
to get
and that
excited about
one,
it.
if anybody was paying attention to the James Webb Telescope launch, which I was, and I bet you a lot of our geeky audience was, the stakes were so high,
Yeah,
like, because if it blew up or something went tragically wrong, the time it would take to redeploy was unfathomable. The stakes were so high, it's like they had one chance and it had to be perfect, which is why it took 10 years, but it could put them back another 10 or something. Um, so it really was a marvel to behold that they were
yeah,
able and we're talking thermal, power, fuel efficiency.
exactly.
I mean, so many things in that system to model. So it really is the ideal thing to look at and against the complexity of the things we're developing, say,
Absolutely.
for radar or cell phones. And so,
Right.
you'll like this because on my side, Murthy, on the board side, I would RF engineers would come to me and say, "Why aren't the simulations I'm doing matching the board you're giving me?" And I'm like, "Oy vey, the things that I have to tell you from the board side that we can do that's gonna screw up your performance number, but they're blind to you. So you have to make sure you put the board effects in there in your model too." And
Yes.
so, I've seen pieces of this, and it really is true that I wrote a blog once that the title was "Slow Down to Speed Up."
Oh, yeah.
And
Yeah.
that's what I hear you saying. It's gonna cost you a little bit of money. It's gonna slow you down at first, but long term, like you said, your confidence curve is gonna go straight up and your time to market is gonna get better. But it's not, we haven't baked this into in our psyche, I think, as an industry yet, but we're
Yeah.
getting there, aren't we?
Oh, yeah. Absolutely. The system level problems, um, unfortunately, are so expensive to address than the problems in the small circuits. I mean, circuits can create problems. I'll give you another example that I came across in my career. So this company was putting all these towers in various the communication towers, right? So they have these amplifiers inside, and they didn't simulate much. They just somebody designed, and then they said, okay, it is working in the lab, and then they took it there, and then they put it there, and then each amplifier started what we call thermal overrun because of the proper biasing, sudden changes. And they said, okay, we are going to make it corrective. We're going to correct it. So they already installed, say, 500 installations. Just this $5 amplifier
Oh
to
gosh.
replace on each one of those towers. costed them $10,000. it's it's expensive. You had to send a person, go in and replace it, and then again test it that it works there. It's going to be expensive. So the system level problems need to be addressed upfront. Otherwise, it's going to be really nightmare for designing. That's why I like this concepts of digital engineering, the digital twin that the concept has come in. We have to shift as much as possible to the left before we go and then do the test.
And then we have
That's
that
the
single source of truth that
Yeah,
lives on, right?
exactly,
And if
exactly.
another engineer works on it or whatever, you have all that record and you have all that good, rich data,
Yes,
um, that you can keep. So someone doesn't have to reinvent that painful wheel again. You have this
right,
single
right,
source of truth, which is a wonderful thing.
right,
All right.
right.
Well, we're going to talk
Um,
more now. Go ahead.
I just want to add one point though here. Maybe we can come back to it. You rightly said about the circuit board and then not taking into account the parasitic effects of the layout and things like that. Um, Even after you take everything, let's say you design, you nowadays integrated circuits are designed to such a accuracy. After you go and fabricate, invariably 99%, maybe 90%, they work the way they are simulated, right? Because of the simulation tools that are out there in the market are so accurate. So circuit level, we are seeing good progress. You can predict, you can get the same answer when you measure. But the issue is you can't use now let us say you have 10 circuits, you have to put them together. Each circuit takes finite amount of time to simulate. That is okay while designing that single circuit, but when you put 10 of them and then you have to run
Yeah,
through thousands or even hundreds of thousands of simulations, the simulation time goes through roof. So
I bet.
the solution for that is convert your circuit level. You should be able to capture the behavioral model of your circuit and then put that and then integrate. Now, this behavioral modeling is a big thing in Keysight technologies. That's what
Okay.
I like about it. That the tools that I use, and then that's what I share with my designers. Please slow down a little bit,
Yes.
and
Slow
then
down to speed
create a
up
good
and
model.
save money. Yeah.
Create a good model, behavioral model, and then if the model can come from measurements, that's what Keysight does. A lot of measurements, bring those measurements, model it, and then you have a much better picture. And then when you do the complete overall system analysis, your simulation time is manageable. I will not say it is lower, because now you're able to simulate. You can say a lot more
Right.
statistically whether the system is
Mhm.
going to function or not. So there is that trend is also going on.
No,
Behaviorally
it's
modeling
good that you
and
brought me back to that simulation
Mhm.
of the system. I interviewed, Anurag Bhargava, your
Yeah,
colleague,
yeah, my colleague.
and we talked a lot about the heterogeneous designs and the challenges.
Yes,
In his case, he was working on RF modules, and
yes,
stacking those technologies and getting them to play well together is a real challenge, and more, I
yeah,
think engineers are going to have to face.
right.
Maybe what they learned in college and this and that, but the complexity of systems is gonna force us into thinking about, heterogeneous integration. And so I appreciate you bringing that back to the forefront. Okay, now let's shift to the 5G. You taught me something, and maybe our audience knows because 'cause I'm always learning, but can you help me understand where we are with the 5G TN, and then you've taught
Mhm.
me 5G NTN. So can you start by defining the first one, and then we'll jump into the other one for sake of this conversation?
Right. So anything on the terrestrial, right? Of course, something um, traveling in the train is still terrestrial. It is moving, but it is all the base stations are stationary in a terrestrial network, and then the user equipments they can be moving, they can be stationary, they can be computers, they can be iPads, they can be phones, they can be anything. User equipment. They can be doorbells, and then
Yeah.
video,
Anything on
IoTs,
Earth.
anything on the earth. So that is all the terrestrial thing that we are talking. And then the communication between all these devices is orchestrated, monitored by the network. That's what we call the terrestrial network. So what happens is, in all these systems that I deal with, uh, invariably there is something that radiates, we call transmitter, and something that receives, we call the user equipment receiver. So yeah, and in between, of course, the space that's hostile to helping these to talk to each other. We'll come to that as well. But uh, the network, what it does is, it's not just one base station talking to one phone, right? It's one base station talking to 100 phones, and there are 100 base stations. And then which base station, as the phones move, each base station should be able to hand over to the next one. So all these operations have to be orchestrated um, by some intelligence we call network.
So
So
that
this
is
is
the
the
TN, the
network. That is
terrestrial
the
network. 5G terrestrial
yes,
network is everything you just described.
right. So the network that controls, that helps the communication between all the terrestrially located devices is terrestrial network. Now, what happened is, in the past 10, 15 years, we are seeing launching things into the space has become much cheaper and easier. And then, the technology has improved. The cost per kilogram to launch into the space has come down dramatically. Um, so that now people started thinking, okay, we need another promise for 5G. I said one of the unfulfilled is ubiquity. The promise was, we will make sure everybody is able to talk everywhere to everything, anywhere, anything.
Mhm.
But that was not really possible with 5G because of the costs and then certain things that came in the way. So suddenly now people started thinking, why don't we bring the satellite communication technology into this fold of the wireless? There were already GPS phones. The people had
Mhm.
very expensive, right? If you want to make a call, probably $10 per minute or whatever it is. But if you want to really establish the ubiquity, you need to bring in new technology. So they thought they will exploit this non-terrestrial objects like satellites. It can be
Mhm.
a drone, it can be a plane, anything out into the space. But again, somebody has to manage all those devices as well. That is the non-terrestrial network,
Okay.
NTN. The problem is, there are two networks now, like two intelligent people controlling two different systems, but they have to hand over to each other. That is the handing over a
Okay.
call from terrestrial network to non-terrestrial network.
Got
That's
it.
what is broadly the NTN.
Well, Murthy, when I think about that handoff you just mentioned, the terrestrial and the non-terrestrial, uh, bandwidths, how do you get those to communicate, and what are the challenges, say, to the engineers in our audience, that may be developing? We've been talking about IoT for years and years and years, and almost everything has wireless in it now. So what are the challenges, specifically for our audience, and also bandwidth issues, and how that applies to the digital twin and simulation you've been mentioning? Let's put those 2 ideas together.
Hmm. Hmm. So the challenge is, of course, it's like two, as I said, if you put two intelligent people together, they will never be able to communicate properly. They conflict each other, and then I want to
It's like
do the
putting
things
2
my own way,
engineers
and
in a
then
room. Yeah.
exactly. But how to bring in the coherence between them is a big thing. It's a lot of, you don't want to modify the terrestrial network already designed and then there, and then your non-terrestrial network software you're writing in it to be very compatible with this terrestrial. So it's more in the software realm, but it also brings into the physical. world as well as the challenges, right?
Hmm.
So um, they're designing the link, what we call, for example, one way is I want to communicate, I want to talk to somebody somewhere, maybe sitting in Himalayas. Let us just simply say that. um, I can make a call. It goes through my base station nearby, and then it connects to the satellite, and then the person in there in the remote area can, it's what we call direct to phone, receives the signal from the satellite, right? So this is a lot to ask for. There is so much going on here. The signals can be very weak. Because you don't have in the phone, you don't have too much power to transmit to the satellite, and then also the satellite to the ground is a lot of loss, tremendous amount of loss. So we had to model all these things, and then in addition to that, um, when these satellites fly, there are other effects. It's not just the loss; it is because of the motion that translates into some complexity in the signals. We call them as Doppler effects, and then the delay. We had to take all this. We had to synchronize a ton of things for the call to be a to be mature. And let's say we are communicating, and unfortunately, the area that the person remotely he was driving, let's say, and then he gets into an area where there is a base station. So we don't want this link to be again going through the satellite. How do we how do we move that call from this non-terrestrial link to the terrestrial link? Because now suddenly the base station can, we have this beautiful terrestrial network in the world, right? When I do this, it goes to the base station, and the fiber, and then fiber through the ground, and then through the ocean can go there, connect to another base station. So there is a lot that happens in handing over. So the, this also should work flawlessly. Everything, both the networks in terms of their intelligent communication, accepting what the other network is telling the network, and then in the real world, the signals, their losses, and then their quality, all these things accumulate. It's a lot of challenge. And then, of course, I'm not saying that I have knowledge of everything that goes on there, but what I know is electronics part of this is what we deal with in Keysight, and then what we deal with in our simulation modeling tools that we give the industry. We design the electronics in here, and then this electronics is so you have to model it so accurately in order for you to be able to predict. And then modeling accurately, I always go back there, uh, building the behavioral models and then simulating them. And then another important thing is this channel between them is so dynamic. Um,
Hmm.
I tell you that the dynamism of this channel is so important. Let's say you're holding your phone, you're talking, and then the base station is communicating to you. And then we have some advanced concepts in 5G, what we call beamforming. So it can actually, previously in the older wireless technology, the base station was transmitting everywhere. And then, okay, user, if you can pick up my signal, pick it up and then go do whatever you want. That was the attitude. But the base stations have changed. They now say, okay, I'm sending my energy directly to that user. The information the user has to receive is so pointed towards the user. It's much more gain, and then much more less interference because of that. So the user is able to receive very easily. Now think of the user is holding the phone, so the beam is coming and then pointing, just turns his head, turns around, everything is gone. The whole process has to start, and then we have to again make sure the base station and the user are communicating by through these narrow beams. This is one of the biggest things that to highlight in 5G world. The challenge is they thought, okay, we can do it in millimeter waves, 28 gigahertz. We have a lot of antennas. We can put them on the phones and then on the base station, and then we can do all this. But they realized this. beam management, what we call one of the biggest things, is not easy. So that's what anyway, that's what they're trying to tackle, and then they're going to tackle that a little bit more intelligently into 6G. That's what is happening. So these are some of the challenges, the procedures, the way we manage the things to counter what the space in between the transmitter to the receiver happens, and then the environment, so many devices being there, all these things were problematic. uh, Again, the thing in the beginning I said, the technology is reaching the common man, that only then it will be successful, only then the cost of um, being able to operate will come down, and then only then the companies can make money, etc. You won't believe, the how much of course. In USA, for wireless plan, typically you pay 50, 60, maybe 80, $100, depending on the provider. It's not that much in those countries. They pay maybe one tenth of what we pay, but they still get the same quality, right? Because of the massive adoption by the population, the companies can still make money.
Right.
So that is the important thing. So um, for us, some of the things that 5G, with all these challenges, 5G, if it fell short, it fell short because of the adoption, the return on investment for these companies. So what they have to do is, how do we make this more technologically acceptable, in the sense, how can we bring the cost till I can make money? That's what, if AT&T, Verizon, and then all these people think, they have to find new use cases. So as you mentioned, the IoT, that's a new use case. What if we provide a service that monitors these devices everywhere, especially the critical infrastructure, the mining, the shipping, you're shipping these things. So through the NTN, if you can monitor all of them real time, and you can make money, then of course you can invest that into the other side, and then make the promises of 5G more uh, more thoroughly fulfilled. So the IoT is the most important thing, and then what it offers. Terrestrial IoT, we do have, of course, all of us, doorbells, and then everything, we have cameras, and then everything that is becoming more and more common compared to what it was 10 years ago. Uh, but the critical infrastructure, and then offering those services will bring more money, because it's an industrial use case for these companies, and that is more reliable. What happens if there is a hurricane, if there is a twister?
Right.
Suddenly the terrestrial thing can be broken, but from the satellite you can still beam, and then you can still receive the signal, and then you can still be reliable and resilient. So this is the important thing that they are trying to do. So balance the use cases, make money in one area, use the same infrastructure to cater for the other before it matures. That that's
Well, I
uh,
think
that's what is happening.
maybe because of COVID and all the disruptions there, the idea of protecting countries protecting their critical infrastructure
Mhm. Yeah.
became a big topic that anybody can hear in the news on a fairly
Yes.
regular cadence, that
Yeah.
this is disastrous because we are so dependent on the terrestrial network now. And then there's geopolitical things and on and on and on. And, you know, uh, people need, heat and water and communications and all these things in an uninterrupted way because there could be loss of life. So, I think that's certainly driving it. And when you're talking about keeping those costs down, is your thesis here then that by shifting left, it helps bring those costs down, which
Exactly.
allows sort of a buy-in across and to scale and to be affordable to companies that are investing, making these large investments.
Exactly. We have been in a constant pressure to deliver the systems are becoming more complex. They're becoming larger systems, and then but still. The end users expect, they don't want to pay more. The industry doesn't want to pay more, but we have to do that. So you're under constant pressure. You have to deliver in time. The time to market is so important. So there are so many pressure points on the engineers.
Mm-hmm.
They that's why I won't blame them if they take shortcuts. I want to go to the lab as soon as possible and then test it out. And then anyway, I have to test. I'm going to fix the problems there. That mentality is okay, but it's not for the modern era of developing systems, because systems are more complex. You can't take the same approach and then build the inherent inefficiencies and then think that, okay, this is the cost. No, that is not necessarily, that has to be the cost. You
Mm-hmm.
bring it, shift left, see how much you can save. All that you have to do is apply to one project and then reap the benefits, and then you will see, going far into the future, the benefits of. And also there, I would not blame, I would not just underestimate, um, even in simulation and modeling, there is a by and large, there is a part of science, there is a part of little bit of art as well. That's your knowledge, your
Mm-hmm.
experience, the way you set up, the way you run. You can get things done faster, you can get things done more accurately by little bit common sense. Even in the PCB world, I can give you an example, that because you brought PCB. So all these electromagnetic tools, they give you very accurate result because you're really going into the physics and simulating what happens inside.
Mm-hmm.
But if you're designing a filter, and then, depending on the tool you use, the center frequency of the filter can be underestimated or overestimated based on the tool, the technique you use, whether it is a momentum. Maybe Anurag might have mentioned these things. Um, it can be higher and lower, but an experienced person, I have seen this, literally with a lot of users there. Oh yeah, I know how much it is going to the tool is going to shift, so I will just design for a slightly different frequency so that when I measure, it is going to be at the frequency I want. It's a very
Right.
tiny fraction, but very clever. And then that is the art they learn. So there is a little bit of art you have to apply as well for simulation modeling to get what you want. But once
Right.
you master that, your costs are going to come down unbelievably, controlled. You don't have to toil too much in the testing world initially. Of course, final test is nobody can um, eliminate. We should not be avoiding any testing. It has to be done thoroughly. Only then you deploy. But designing it upfront, that is what shifting to the left is so important for all these systems.
Well, if in our audience, if there's any of you engineering managers out there, here's a gem for you. Make that case and that fight, because often the engineers that are designing circuits or designing the circuit board or just looking at the signal integrity, we get into these silos because of the complexity. But if we don't have that those systems in place across the system, then the whole
Yes.
thing's broken. So, again, you invest wisely to save and scale, so there is a win. It's just there we're I say I always have engineering empathy, Murthy, and I bet you have a lot of engineering empathy too, because the
I
pressures on engineers today
Oh,
is
yes.
insane,
Yes.
to save money, to do it faster, on and on and on. Um, but I've been beating this drum way, way, way downstream at just the little circuit board level, of how much time and money can be saved. But that's true all the way back to the concept of the device, all the way through the system. So engineering managers, think about this one. I'm sure you have tools and all that, but I think things are changing and we have to pay attention, especially with critical things like 5G. Okay, now for a fun question before we wrap. And thank you so much for your time. This has been such an interesting conversation. Okay, we're having trouble, getting 5G and getting the terrestrial and the non-terrestrial to communicate, and line of sight and beamforming and all these things we've talked about. but you hear it all the time, Murthy, them talking about 6G. So what what's coming? What do you see that's ahead? Because I always like to ask this question of Keysight people because you guys are always way out there on the leading or bleeding edge and often sit on standards committees, and you see this ahead of the public. So I'd be very interested, in you sharing with our audience what you're seeing.
Sure, sure. What comes to my mind? There may be a lot of ways to answer your question, which is many different angles. But the angle that I take is um, 6G. The first thing that is going to happen is these two networks that I mentioned, NTN and terrestrial and non-terrestrial networks. They are going to be not anymore two separate entities. In 6G, they are designed to be one
Mm,
entity. So you, by design, so in one intelligent head. There are not two heads now.
okay.
One thing. So that makes, I believe, for the people designing and developing, it's almost like going back to the drawing board and then designing the whole thing, right? So that is 6G. So they're going to merge 5G and 5G NTN and TN, and then it's going to be one single network in 6G. That is for sure is the biggest thing that will happen, and then that opens up a tremendous amount of opportunities and use cases. Um, some of the use cases, they're very interesting application. Like 5G, we said remote surgery, and then the other things we said. But here 6G, it may bring a little bit more interesting stuff because as the frequencies, 6G is going to happen very higher frequencies, a lot higher than what we are doing today. And then the higher the frequency, one big thing, one benefit we get immediately is most likely it is unused frequency. So for the
Mm,
governments, they don't have to find new spectra, they can sell. And then possibly all governments together can sell the same spectrum to these people because the 5G implementation in the USA is a different frequency band. So it's slightly different from what is in
mm,
Japan, what is in Europe, and what is in China. So everywhere the systems are different. But probably they can give the same frequency and same frequency bands that will unify development to all systems for that particular band, so there are not too many things. That's one advantage. And the larger the bandwidth, you can send a lot more information easily. That's communication theory, all of us know. But more than that, what it is going to fuel, the way they are saying, there are 5 or 6 fantastic use cases. um, Number one is the the basically, because all this beam management that I mentioned, and then also
mhm.
the way the user equipment communicates to the base station, it has to send some information, what we call channel state information, things like that for them to reliably operate. Um, they they are so dependent on so many parameters, hundreds of parameters. That means parameters that are dynamically changing. That means your algorithms, whatever you have today, they have to operate very quickly in real time. That is the problem with 5G. We could not come up something that will manage less than a millisecond. Because as I said, I turn my head, everything is gone. I have to realign my beams for a reliable connection. So that is what is in 6G world, everything is going to be based on AI/ML, artificial intelligent machine learning. Everything,
Wow.
literally. So that is a fundamental shift. So when you say artificial intelligence machine learning, what is going on here is, by nature, the way neural networks are designed, they can handle hundreds, thousands, maybe hundreds of thousands. Now we are hearing millions of parameters easily. They can absorb, they can react, and then they can predict what needs to be done. So that could be the solution for these intractable problems today. So that is going to happen. Somewhat it is coming in 5G, but that is fundamentally 6G is based on AI/ML. And let's come to the use cases, very interesting use cases. As I said, autonomous driving, right? You're driving in a car. Today, if you are in San Francisco, very interesting, the Waymo. You can order and then it comes and picks you up. But the what is that Waymo car is able to see is what is visible to it. When I
Right.
say visible, it can be optical, it can be microwaves, but everything is that is visible. Something is behind the building, it cannot see. Somebody walking through the street and
Yeah.
suddenly comes, it cannot
Yes.
predict that somebody is coming.
Yeah.
So there are many, many things that are going to be missing. Whereas in the 6G world, everything is connected to everything. And then there are so many sensors that are communicating, not the sensors on the car actually acting alone on their own, but these sensors are communicating, and the network will have a picture of what is the surrounding of the car, not just in the visible region, but beyond that. So once the network knows, it knows how to drive the car much more intelligently. If somebody is coming, it will say, okay, stop or slow down, or somebody is coming, it can caution. So it is going to be more realistic. So how are we going to sense these things? It is all radar technology. It's a wonderful thing. The communications and radar world are going to merge in 6G. And there are a lot of research that is going on, very exciting research that is going on to bring these two technologies together in the way of creating new waveforms, and then new techniques, and then so the sensing and that's what we call integrated sensing and communication, ISAC. It's a use case. When that happens, you know everything everywhere. Probably even when not just the cars, when you're walking on the street, something is happening, you will know what is happening in the next street. You can literally, the network can inform you whatever is going on around you if you want to know. The other application is, there is a transmitter, there is a receiver. That's all we are dealing with in the communication systems. So when the transmitter tries to communicate with the receiver, it transmits these waves, and these waves are going to be attenuated. They can be reflecting off the buildings, and then there can be other radiations coming. So what comes back into the receiver is not just what the transmitter sends. There is a lot more that comes back, and then all that interference, all those things can cause what we call deep fading. That means signal can fade, so you may not get anything, or you may get better signal. That's both things can happen. So the receiver receives the signal, and then it estimates what is going on in the between the transmitter to the receiver. That's what we call channel estimation, right? And it conveys how good the channel is to the base station, and the base station in turn will modify the waveform. It'll say, okay, I'm not going to communicate to you at the very high speed, but I'll reduce the speed, because reliability is more important than the speed. Right? Always we say safety is more important
Right.
than being able to do fast, or drive faster. So same thing applies here. So what is going on here is, the the channel. We are trying to counter the channel. We are living with what the channel is. In 6G, it's total shift. What if I quote all the buildings? This is typically more problematic in the urban area, right? I go to New York or San Francisco and then quote all the buildings with electronic quotings that I can control. So if I can control those, what we call intelligent surfaces, programmatically, how it should reflect, where it should reflect and send the reflection. So if I can coordinate all the reflections, combine in such a fashion to the receiver, suddenly the receiver receives beautiful signal, wonderful high signal to noise ratio. What it means is, we are taming the channel. We are creating our own channel. We are not living with what is happening. We are
Right.
creators of the channel. It's like
Right.
God creation, right? So
I
that
was
is another
just,
application.
don't
It is
you?
called,
I know because of how long you've been in the industry and how long I've been in the industry. I'm not sure a 30-year-old would appreciate it in the same way, but boy, for people like you and I, it feels like science fiction unfolding
yeah,
right in
yes,
real time, and it always amazes me how much the human race and technologists and engineers have been able to do in a matter of decades. Um, it is just truly stunning. And the pace of information or the pace of innovation is speeding up. And I'm sure it's going to be powered by these technologies you're talking about with AI, ML, and gosh, it's something to behold. But then as you said, finally we're going to deliver in 6G we will deliver on the ubiquity that we've been promising all
Yes,
along because
absolutely.
we've eliminated the limitations of line of sight and beamforming and those things, and we now have the terrestrial, and we have the means to have 2 intelligent systems, communicate flawlessly. That's amazing. Well, Murthy, I've taken so much of your time, but thank you so much for sharing your vision, your wisdom, your engineering knowledge, and what is here now, what engineers can do to get better. And where can folks go to learn more about this and engineers that may want more information about the intricacies? I know you have an amazing knowledge library. Where can folks go to learn more?
People can go to keysight.com basically, right? The search engine is wonderful. If you ask for whatever you're looking for, 5G NTN, let us say, you type it and then it should automatically come. There are sometimes keysight.com/find/5G NTN, as simple as that. It will find the whole web page dedicated for 5G NTN. Similarly, we have page dedicated for 6G, and then pages dedicated for radar. So you can really jump in, get all these things, and and also look for sometimes under the support. You do have learning tools, lot of learning tools. So you can also search for solution briefs or application notes, product notes. There is always a ton of things. Very specifically coming to the area that I deal with, because
Mhm.
Keysight is a big ocean. If you go to the Keysight, there is the products, and then there is the software. Under software, design engineering tools, and it shows the entire portfolio of our tools. And you can get in there very specific areas. If you're doing a circuit, you can get in there. If you're doing a system, you can get there and then ask for it. So there is, it's always easier to get there and then find. Um, if there is any specific question there, we are always very happy to very quickly answer. Just enter your question under the support, contact us, or there is a place, and we our field is worldwide, very ready to get you all the material that you want.
Well, thank you again, and I will get, for our audience, I will get with Murthy and pull a couple besides all the things that he just shared, I'll get a couple very specific to our conversation. I'll put those in the description and the show notes, so make sure you go check that out. Murthy, it's been a delight to meet you and to learn from you, and thank you for all the insights you are giving, to us in this conversation, not only to the practical consumer devices that we're facing, but also how engineers can solve some of these problems and these complexities they're dealing with daily, and just sharing your knowledge and wisdom. Thank you much. Thank you so much for joining the show today.
Thank you, Judy. Thanks for the discussion. It's very exciting. Always a pleasure to share.
For our audience, make sure you go check out the description in the show notes. I'll put all I can for you there. And we will see you next week. Until then, remember to always stay connected to the ecosystem.